Hello, hello participants. Yeah, so we will start in another few minutes. Let's wait for some more time for others to join. Okay, without much delay, we can start today's session. So, a very good evening and welcome to today's tutorial session on urban utilities planning, water supply, sanitation, and drainage. So I think both of you are here have been attending most of the weekly tutorials. So without much introduction, we will directly proceed ahead into today's discussions. So this week, sorry, this was week six. Yeah. So in week six, what we discussed was about water quality and water treatment. So we went into great depths of this on different water quality measures and water treatment measures. So let's try to solve some problems based on this. So this, both of you already know. After each question, we will have a small discussion on the question, and then we will proceed on. And last, we will have an overall discussion. So here, this week's week six session, we do not have much problems, or in fact, we do not have any problems. It's mainly theory questions which we have to solve or try to reason out. It's a very simple assignment which is there this week. I think you both would agree with me in this also. So it's mostly what we have already learned in our previous classes. We are brushing up and we are learning something more. So let's get started with that. So starting with the first question, match the following and mark the option for the correct match. So the question asks about wholesome water, palatable water, and potable water. And the question asks us to match all these. So how do we go about this? So San, can one of you give their opinion on what do you think the answer is for this one?
A or C, both are same. You can see your option A and C.
Okay, yeah, both are same actually. Uh, One second, just give me. Is it my typing mistake or was it already there? I'll just check. Okay, no, I think that is a mistake on our part. It's not a typing mistake. The question is like that. Yeah. Okay, so A and C both talks about the same answer, right? Yeah. Okay, same thing. Fine. So let's just discuss that. Uh, so yeah, so we have already discussed this in our lecture. So just for this question, let's go deeper into this. So potable water actually comprises of both wholesome water and palatable water. So the whole definition of potable water is that which is a combination of wholesome water and palatable water, and it should be fit for human consumption. So whatever is fit for human consumption is mainly called potable water. And it also follows certain standards, because how do we measure whether it's fit for human consumption? So based on the amount of minerals which are required, based on the impurities which are not supposed to be there, based on the tolerance level of certain impurities, standards have also been decided for this. So based on IS 10500, based on the list of chemicals or components which are there in that, we can say whether it's fit for human consumption or not. And whichever follows this standard is known as potable water. And in this potable water, we have wholesome water. So wholesome water is the first level where you have all the impurities which has been removed, and it is not harmful to the public. But so this is just the removal of impurities is there in wholesome water, and certain components which are actually useful, there is no need to remove that also. So for instance, what are the things that should be removed is that you should remove all the disease causing bacteria, and it should be colorless, and it should be good, and it should be tasty and odor free, like it should not have any bad odor. So it's, it's the wholesome water. And again, it should not have impurities which can even corrode pipes. So those kind of impurities should also be removed. And other objectionable matter should also be removed, like organic matter and other matters which can cause harm to human life should be removed. But at the same time, having dissolved oxygen and free carbon, it should have dissolved oxygen and free carbonic acid so that it may remain fresh. So that is important. So you should not remove everything, and even if you're removing everything, then you should have some components like dissolved oxygen or free carbonic acid which has to be added. Now, when it comes to palatable water, it's like an other like upgraded level where it is water which is at a desirable temperature, free from objectionable matter, color, and turbidity. So this is an improved version of it. So yeah, so let's see the question. So we have already answered this. Supriya has already answered this rightly. Sorry, my slide's not changing. Uh, okay. Okay, am I back online now? Uh, Okay, I'm back online. Yeah, that's great. Um, yeah, okay. I do not know what is happening. So today there's some issue that internet just keeps going off and then it comes. So I might keep going like that. I'm sitting in my lab, but still there's some issue in the internet. So I'm really sorry for that. Uh, let's see. Yeah. Okay, thanks, Emma. So let's continue to where we were. So yeah, so this is where we were. So we have Supriya has already answered this. That is, so it's either option A or option C. So here, one sec, it is very slow. Yeah, so either option A or option C, both are the same thing. So both are right. So yeah, let's proceed further to the next question. There is, because of the internet, there's slight delay in my slide changing. Yeah. So next question. Colloidal impurities in water can be removed by which of the following methods?
A,
Sedimentation, uh,
option option D.
option D, you're saying.
Yes.
Coagulation. Okay. Is there anybody else who wants to add in something? Okay. ML also says option D. Fine. Let's
Is
see.
it a multiple choice
No,
question?
there is only one answer for this. There's
Okay,
only one answer
coagulation.
for.
Then it is coagulation, I guess.
Yeah, actually, I understand why you're asking, Emil, because yeah, it is not just one single process. You'll have multiple processes coming after that. So, coagulation followed by sedimentation. So there will be a multiple processes coming. But here,
Yeah.
the most important process is what is asked. So yeah, so you're saying coagulation is the answer. So firstly, what are colloidal impurities, or what are the different types of impurities which are there, and why is it that colloidal impurities require? If you're saying D, then why is it that it requires coagulation? Any reasoning for that? Okay.
May I?
Yeah, you may.
Colloidal impurities, those are kind. No, my uh, answer will be wrong. But still, I'm saying the colloidal impurities are suspended particles which. No. Leave it. My definition might be personal.
It's okay. You can attempt. Okay, Rahul says something. Rahul says final pieces, I suppose.
Particles,
Particles. Okay,
particles.
final particles require more time of settling. Okay, fine particles. Sorry, I read it wrong. Fine particles require more time of settling. Okay, that is a that statement itself is right, like fine particles, but how is it related to this particular question?
Mm, I guess means by coagulation it can be
Particles
removed faster.
charged.
Okay, colloidal particles. So Rahul is saying that colloidal. So first he's saying colloidal particles are fine, and these fine particles require more time to settle. So because it requires more time to settle, so Rahul, which is the option that you're choosing? Like, okay, so Rahul also says D. So I think all three of you have agreed with D. So let's one sec. I'm getting some echo in mine. Is it from this one? All right. Yeah. Okay. So yeah, so let's now see why this is. So yeah, so there are three types of impurities. We have discussed this in our lecture. So we have suspended impurities, colloidal impurities, and dissolved impurities. So now, in suspended impurity, so when we are mainly talking about size as a matter, because Rahul was talking about size, so it goes in this order that suspended impurities have a greater size than colloidal impurities than dissolved impurities. So it goes in this order. So colloidal need not be the finest. Like you can have dissolved, which actually gets into the molecules and into the matter, and it's completely dissolved in that solvent. And when it comes to suspended, we know that it is suspended and you can actually see like the particles are separated out. So impurities are so dispersion of impurities are dispersion of solid particles that are large enough to be removed by filtration. So that is what is suspended. That is, you can see it and you can filter it. And in another definition, you can say that suspended impurities have the same specific gravity as that of water and are mixed in water. So because of that also, you can easily uh, remove it using filtration. Now, the measure of this is turbidity. That is, because of suspended impurities, we call turbidity is there. And I'm not audible. Oh, okay. Hello. Okay, fine. It's audible. Okay, audible. Okay. So, I think maybe sometime my net went low. I'll continue from here. It's breaking. Okay, I think you'll have to bear with me now. I can repeat in case you didn't understand anything, so I can repeat. So let me continue from here. So yeah, so these are what suspended impurities are. So in simple words, it's large enough. That's it. And dissolved impurities, as I said, it is smaller. So these impurities are dissolved in water, and usually it is come from rocks or soil. It moves over the rocks and soil, etc. So in water, usually there are different solids, liquids, and gases which are naturally dissolved in it. It's also. So here the question talks about colloidal impurities. So now how is this different? Is that these are very finely divided dispersion of particles in water. So it's again, it comes in between. And these particles are so small that these cannot be removed by ordinary filtration processes. And these are not visible to the naked eye also, so we cannot easily remove it. Also, these colloidal impurities, they have an electric charge associated with it. So the colloidal impurities are electrically charged and they remain in continuous motion. Sorry, I went to a different slide and it's not changing. Just give me a minute. Yeah, this is a bit sad. Yeah. So yeah. So these are now why is this charge happening? So the electric charge is basically due to the presence of absorbed ions on the surface of the solid. So what happens here is that these particles, as discussed, they do not dissolve completely, but they get attached to the surface of these solids. So they are basically trapped over there. So because of this, there's a charge which is these particles are charged. So this can be the both positive charge and negative charge. So acid or neutral particles, they have the negative charge associated with it, whereas basic materials will have the positive charge. So some of the examples are that for negatively charged, you can have silica or glass, which has a negative charge associated with it. But basic oxides, such as aluminum oxide, iron oxide, etc., have a positive charge associated with it. And these charges on the surface of the particles are large enough in comparison to the mass to cause the particles to repel each other. So, like if there are two like charges, they will repel. So, this repulsion is what causes this continuous motion which is happening within these colloidal particles. So, yes, so due to this repelling actions, all the colloidal particles remain in motion and they do not settle. So this is because this is why the removal becomes very difficult because they are always in motion. So like filtration or sedimentation, we cannot make them settle and we cannot remove them off easily because they are continuously in motion. So these are generally associated with organic matter containing bacteria, and sometimes and mostly they can cause epidemics also. So this is a brief description about what colloidal matter is. So now because of this, we need special methods, or we need a better method in order to remove other than the normal methods that we use. So in the options, we have the normal methods such as sedimentation, filtration, and disinfection. So this we've also discussed. In sedimentation, it's simple. That is, we allow it to settle for some time, and all the flock settles to the bottom, and all the clean water, which is clear water, which is there on the top, is removed. So that is sedimentation. Filtration, we normally filter it out. So there are different kinds of filters we use, like very fine filters like sand, or we can use gravel or charcoal, and with different pore sizes we use, and these are used in order to remove all these dissolved particles also. And sometimes we even, for other dissolved particles like just salt and all that, we even use evaporations. That is, we evaporate that water, or we evaporate that water off, and we get this material out of it. And also the other method of disinfectant we use, such as chlorine or chloramine, which are added. These kills germs at the same time. So it settles and we can remove that off. So these are the normal methods of water purification. So now here we are mainly talking about coagulation. Why? Because in coagulation we can add chemicals with a positive charge to water. So chemicals with a positive charge are added. So we already discussed of how these so we already discussed how colloidal impurities are charged. So because these are charged, now we use coagulation so as to, this slide is getting a bit, yeah. So we use coagulation, so we are adding up another charge to it. So because of this, dirt and other dissolved particles bind to these chemicals and they form larger particles, and this helps in again using our normal process of sedimentation. So so as Emil was saying, that mostly coagulation is always accompanied with sedimentation or clarification. So coagulation alone cannot remove it. After that, we need to do something. So as he that I think that is the reason why he asked, is more than one option right? So yes, so it is a continuous step process, but then here what we are mainly focusing on is the main process that we're using, which is coagulation. So without coagulation, we cannot use sedimentation. So yes, so coming back to the question, our answer is coagulation. Okay, our answer is coagulation. Cool. Yeah, let's proceed to the next question. Was there any doubt in the previous question, or shall I go ahead? Was I audible?
Yes, you were audible and it is clear. You can go ahead.
Okay, cool. So, yes, so this is match the following and mark the correct option. Protected deep wells free from facial contamination, protected lowland rivers with low facial contamination, unprotected shallow wells with facial impurities, and unprotected watersheds with heavy facial impurities. So, can somebody attempt this question? Okay, so let's go one by one. So protected deep wells free from facial contamination. what also it doesn't have any facial contamination and it's already protected. It's protected deep wells. So what should be the method that we're using?
Disinfections, second one.
Okay, so Supriya says disinfection. Fine. And now this is the next one comes unprotected lowland rivers with low facial contamination. So which means it's again unprotected, plus there is some facial impure low. It is there, but it's low in level. So what should it be? Any guesses?
Four, it will be filtration and disinfections
Why filtration?
because fecal contamination is there.
Yeah, okay. So there is something. So we will go for filtration and disinfectant. Now, unprotected shallow wells with fecal impurities.
It is three, disinfections, filtration, and disinfections.
Okay. And then unprotected watersheds with heavy fecal impurities.
No, one second.
SS1 is what Rahul is saying. Okay, SS1. So if this is the one which is the so then option D will be the answer. No, that
Yes.
which will be the answer then? Because Q, no, nothing is matching. If what you said is right, then none of the options have that, right? Or do we have B? B has that, is it?
No, 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 it's not.
No, it is not. So let's see what it is.
It
So
is saying R1, but for heavy fecal, can you please go back to these questions? If it is having heavy fecal impurities, then it will be pre-disinfection, filtration, additional treatment, and then disinfections. So S will be one, but for unprotected shallow well with fecal impurities and the Q is having low fecal contamination.
hmm, okay.
So R will be um three only, I guess.
Okay, okay, okay. So you have reasoning it out. Let's look at the theory and then we will come back to this once more.
Yes.
So this is what we learned in our lecture. So it says that for protected deep wells, which is essentially free from any fecal contamination, just disinfection is fine. So this we have got it right. Now unprotected shallow wells with fecal contamination. So this is at low fecal contamination. We need filtration and disinfection. So this also we got it right. So as Supriya rightly said, why filtration? Because there is some low contamination which is there, and by filtration we can remove that off easily. So now the other mainly talks about surface water. So in case you have a protected inbound upland water, essentially free from fecal contamination, then again this only disinfection is required. Then unprotected impounded water or upland river with fecal contamination, you need filtration and disinfection. And now unprotected lowland rivers with fecal contamination, you need a so this we can note unprotected lowland rivers with fecal contamination, you need a pre-disinfection or storage and then a filtration and then a disinfection. So you need both. So from here onwards, for everything, we need both pre-disinfectant as well as a post-disinfectant. Both are required. So now here, so if you observe, it's again when the fecal contamination levels are increasing, more more treatments are required. So again, when it comes to unprotected watershed with heavy fecal contamination, we need pre-disinfectant, storage, filtration, additional treatment. There is an additional treatment also, and then we have disinfection. So now, and then the last one, which is unprotected watershed, gross, which with heavy fecal contamination, not recommended for drinking. Right. So looking at this, now I didn't put that again. Okay, let's go back here and now let's try to answer this once more. I'll just erase this off if I can. Can I? Yeah, erase it. Yeah. No? Yeah, erase it. Okay, let's try to answer this once more. So yeah, we have already discuss this now. So the first one we got it right, that it needs to be 2. So I mean, just eliminating the options, it can either be B or it can be D. Like these are the two options that we have. And the second one, unprotected. So this one also we got it. That is, you need for the second one we need filtration and disinfectant. That is adequate enough. So I think that itself answers. So we have this is the answer. That is second. Let's see the other one. Are unprotected shallow wells with fecal impurities. So that goes to this one because we have un, yeah, we need pre-disinfectant filtration and additional treatment is also required. One second. Yeah, third one, unprotected watersheds with heavy, no, oopsie. I think there's an error in this particular question.
No, no, I will explain you 1 second. See, actually, the P is 2, that is right, and
Yeah,
S
yeah,
is
this
1.
is, yeah,
So
yeah,
Q is having low land river, so it will have uh, pre-disinfection, filtration, and disinfection. And shallow well will have only filtration and
yes,
disinfection.
yes. So
R
this,
is
yeah, right.
R
Correct, correct. You're
no
absolutely right. So it's
B.
one is watershed and one is shallow well. So that is where the mistake is. That is where we need to focus on. It's not just on the impurities, but also on this one. Right, absolutely
D
right.
option is correct. D.
Yeah, B option is right.
No,
Very good.
not B. D for Delhi.
No, no, B is the correct answer. As what from what you have reasoned.
No, it's D. R is 4, right? R is 4. There, R is 1. S is 1, correct. S is 1. Heavy fecal will have filtration additional treatment. Correct option is D. D for Delhi.
Okay, okay, okay.
See, for P
Okay,
and
got.
S, we are sure.
Ha ha ha. Yeah, yeah. Fine. So let's just look here. So
To C for heavy, where it is.
yeah, so unprotected
Unprotected.
watershed wells with it is pre-disinfectant. Yeah, so that is right. So this one pre-disinfectant filtration and additional treatment should go into unprotected watershed. So S will be one. Okay, right, right. You're right. Absolutely right. So D will be the answer. So I think there is an error. So as I was saying, there is an error in this particular question in the this was a previous assignment which was there and if I don't know whether you have access to the previous assignment answers. So if that is there, then there is an error because B is the answer which is given, which was given right answer in the previous round. So now the answer will be D. So there was an error in that particular question. So I think you can make a note of this in case you come across that assignment. Do you guys have access to it, by the way?
Yes, I have seen, but that is
Yes.
downloading to a very low quality size. If I get the print, we are not able
Okay,
to.
okay, okay, fine. Yeah. So essentially this whole discussion tutorial we're doing so that we can discuss those questions because those are already there, right? So established. So, and sometimes there can be errors in that. Like for instance, in this the assignments which are running itself, sometimes minor errors can happen. So like that, some errors. So yeah, so this you can make a note of it. The answer which was given in that particular assignment was B, which was wrong. So D is the correct answer. Right. So very good. That's good that we were able to solve this together. Now let's go to the next one. Which physical property of water is measured by a nephelometer? So what?
Turbidity.
Yeah, turbidity is what you're saying. Anybody else? Any other? Okay, all of you are saying it is turbidity. Let's see. So okay, so what? How do we measure the other elements? Like how do we measure pH? pH? How do how do you measure pH?
Actually, forgot the name. If you give options,
Litmus
I can.
test?
Sorry.
Litmus? pH
No,
paper? Okay.
no.
Okay, Emil says pH paper. Fine. What is a pH paper? Okay, yeah, we learned it in school.
School we are
Yeah.
used to have pH paper.
Fine, yeah. So here in our lecture, this one we were talking about electrometer for it, but yeah, we can use pH meter also and litmus test also. So that paper is called, so to test whether it's acid or basic, we use the litmus test. If you remember, this is what the litmus paper is there, which is a pink color paper, which yeah, litmus paper exactly. Was I not audible? Yeah, this is what I was asking. Yeah, so it turns colored when we put it in an acid or basic solution. So that is for pH. And total solids, how do we measure? Yeah, so for total solids, I think we have mainly in our lecture we have discussed about how do we get it. That is, how do we take it, by what is the process and what it contains and all that. Yeah, that drying test exactly. So that drying test is what we have discussed mainly about total solids. Yes, yes. But drying by filtration, first we suspended solids. First we filter, then we again heat it in order. So we evaporate it, and then we heat it. So that whole process we have learned. Yeah, it's a series of procedure, right? Exactly. So and for taste, how do we test it? I mean, it's Emil says tongue. No, there is another method also to do it. We have discussed in the lecture. So let's just check here. So for taste and odors, mainly it happens because of dissolved gases such as H2S, CH4, carbon dioxide, oxygen, etc. So and also some minerals like sodium chloride, iron, all these components. So we use an odor intensity meter in order to for taste and odor, like it's together. So we use an odor intensity meter. So the threshold odor number, like we have a number based on this. So basically it's done by, so we take a sample, and the amount of additions that we need to add to the sample so that it becomes diluted and the odor or taste is not differentiable is what we are checking. So the sample is diluted with odor-free water, and the number of times it is diluted till odor is not noticeable gives a threshold number or the odor number. So based on this odor number, we look into uh, how much impurities was there in that particular water. So for everything, we have a threshold number which we are using. If my memory is right, we even discussed about that number also in our lecture. Like yeah, so for so there is a threshold number. I'm not able to find it now, but in the lecture we discussed about this, that there'll be a threshold number. So if it is more than that, then we know that there's high level of contamination which is there. And for total salts, so these suspended salts, so how do we find it? It's by a whole process, as Emil was saying, filtration, drying, and weighing. So we take a sample, we evaporate the remaining water, and we weigh the residue. So once we weigh the residue, we get the total solids, that is the dissolved soil plus colloidal solid, what is there, we get it. And if we again further heat it in a furnace, it will decompose and it will give more organic. It will decompose, giving us the inorganic solid. So by measuring this, the quantity of organic and inorganic solids which are there, we measure what type of impurity is there in it. And yeah, so pH, just to revise what we have learned in our school, so it indicates the logarithmic reciprocal of hydrogen ion concentration in water, and it tells us whether the water is acid or alkaline. So two methods which we have learned is we can use the colorimetric method. So we add indicators products and like certain chemicals into it, and based on the color which is formed, we compare it with the standards to know whether it's acid or alkaline. And electrometric meter, so this is what is commonly used, the electrometric meter, because it's very easy. So these have special electrodes which are connected, and in the meter we'll directly get the pH value. So this is what is commonly used. And yeah, so this is what we were discussing. The answer for this is, for turbidity, we use this. Uh, uh, for the question asks why we use nephelometers. So for it is to measure turbidity. Now, why do we? So this is what we have discussed in the lecture. So let's just go a bit more deep and see how the nephelometer works. Also, if we in a in a rough discussion, we spoke about it uses light and the dispersion of lights, or the amount of light which is trapped, in order to find the intensity or the turbidity which is there. So while discussing, we already said that turbidity is a measure of which type of impurity, suspended, colloidal, or suspend or dissolved impurity. Yeah, light diffraction. Yes, yes, it talks about light diffraction. So now I'm asking, turbidity is a measure of what type of impurity? Yeah, right, right, Amber. It is suspended impurity. So which means that these particles are very large, and their presence is noticeable, that we can. So that is why we are being able to use this light test. So nephrometer basically uses light in order to test it. So due to this particle, there is some uh, the light rays in the light rays we can capture that based on this particle there is some difference which is there. If the particles are not there, how the light would be in this light trap. This is called the light trap. And when the particles are there, how it would be, it is different. So this is so here we see the actual nephrometer. So it can be such big in size, or in the previous one we saw the micro portable ones. Sorry, my slide's not changing. Yeah, so these portable ones, these can also be used. These are very, but the physics, to explain the physics behind this is more easy. So basically, we keep our the sample of water over here, and then we view it through this. So there are multiple filters which are happening over there. So this is the bypass RGB bypass filter. So it filters the red, green, and blue light, and it separates that out. And then from there it goes into, and then we have all these other additional mechanisms over here, the different sensors and all. But what is more important is that in the end, when it comes to the light trap, there is the image, or we get a particular pattern based on the impurities which are present. So this is how a nephrometer works. Mm, yeah, so let's go on to the next question. Which statement is correct among the given statements? So basically, they're asking what is total solids? What constitutes total solids? So can somebody give your opinion on what you feel constitutes total solids?
It's B.
Total solids, suspended solid, dissolved solids plus colloidal solids. Okay. Uh, why not? Why not D? Okay.
Because organic solids are added in other three. Organic solids is not. Uh,
Organic solids are not part of it.
yes.
Okay. And ML says it is A. Suspended solids,
No,
organic
no, no,
solids, and
no. Supriya is right. Means I remember doing the test by removing the VOCs, volatile organic compounds. We remove it before taking the total solid test. Supriya is right.
right. Okay. And okay. So Rahul also says B. Very good. So let's just see that your answer is correct, and Supriya is absolutely right. It is already included in that, so you don't need. So it's basically total solids are composed of suspended, colloidal, and dissolved solids. Now, in these solids, you can have inorganic and inorganic and all, but this is the correct thing. Like the different types of solids which are there are suspended, colloidal, and dissolved. So now this mixture includes several like so for instance your dissolved solids can be your sodium chloride, and other suspended solid particles can be silt, and plankton can also be there. So now why is so we were discussing about total solids before also. So why is this important is that a high total solid level indicates that there's high level of solid material in the liquid, and depending on the evaluation criteria, if there's a high level of total solids, this could even be considered the water with high level of total solids can even be considered as contaminated, because you don't need so much of total solids in water. You need some amount of dissolved solids, as we discussed. Some amount it can be acceptable, but more amount will lead to water contamination also. So, and how does this usually happen? Like, how does water get contaminated with total solids? Mainly, it happens when soil erosion is a major contributor towards this. So from soil, it just gets mixed on to the water. And an increase in the water flow rate or decrease in stream bank vegetation can speed up the process. and thus contributing to levels of suspended particles such as clay and silt. So this is understandable. And mostly from other naturally occurring minerals or rocks in soil such as sodium chloride, calcium carbonate, limestone, etc. These also dissolve into the water and it adds to the total solids. So if you see all the types of impurities, three types of impurities that we are talking about is there in total solids. It's just that it is in the solid which is dissolved in water, that is, or solid which is suspended in water, a solid which forms a colloid with water. That is what we're talking about. Right. So that was a very easy question. Let's proceed on to the next question. The presence of nitrogen in water mainly indicates the presence of organic matter and bacteria and dissolved gases, suspended impurities and ammonia, organic and inorganic material. Any guesses? Okay, Rahul says it is A. ML also says it is A. Supriya?
A,
A.
organic matter.
Okay, why not C? Suspended impurities and ammonia. Ammonia is directly nitrogen, so why not? Is it MCQ? It is only one option, right?
Op- Option A, organic matter and bacteria. But
Okay.
because ammonia, even though nitrogen is there,
Sorry, you're not audible. Ammonia?
even though nitrogen is there in ammonia, it is not present in a monoatomic form, no?
Mm,
Is it
okay.
there? I don't know.
Okay,
Yes.
let's see that. Let's see that. See, it is there. In ammonia, it is there, but here mainly the answer you're talking about suspended impurities and ammonia. So the better option over here is organic matter and bacteria. So that's why we will. So let's see this one. The presence of nitrogen, it mainly indicates organic matter and bacteria. So that is the main thing. And nitrogen in the form of free ammonia can be there, like from the first stage of decomposition to recent contamination, it can be there. Then nitrates, organic nitrogen. So all these can be there. It is not just in the form of ammonia. And so basically, all these together forms the organic matter and bacteria form. Like it is there in that. So if you're choosing this option, that is only ammonia and suspended impurities, then that's not the best answer which is there among all the answers. Like when you have an option like organic matter and bacteria, then that is a better answer. So we go ahead with that because this one only talks about ammonia. Like so, presence of water mainly indicates the presence of it is. It does not mainly indicate the presence of ammonia. It indicates the presence of organic matter and bacteria, and in this ammonia can also be there, but that is not the main component. There are many other components also in that. Okay, that is clear. I suppose that's clear. I'm proceeding on to the next question. Okay, yeah. So match the following and mark the appropriate option for the correct match. So this is the different methods that we can use. So silt, scum, dissolved gases and microorganisms. How do we remove? So let's try attempting this. Yeah, Supriya.
D,
Okay, you're D. So which means you're saying silt will go by sedimentation?
silt is sedimented.
Hmm.
Sediment, yes.
And
And then scum is with clarification, dissolved gas is aeration, microorganism is filtration.
microorganisms is filtration. Very good. Yeah, so this is directly from what we have discussed in our lecture, so it's not very difficult. So here we have already discussed that plain suspended impurity like sand and split is just plain sedimentation, and fine suspended matter you can have coagulation flow. So yeah, so here what we are mainly talking about for scum we have clarification, and for microorganisms it's filtration, and for dissolved gases it's aeration. So that is the right answer. Very good. Let's proceed on to oopsie. Uh, I'm sorry, I think. Yeah, so this is the question that we were talking about. Cool. Now, the ninth question. The correct sequence of treatment units for groundwater with excessive iron, carbon dioxide, and odor is. So, yes, so is it sedimentation followed by rapid mixing by chlorine? So, yeah, so what do you think it is? Question 9. Rahul says it is C, aeration. Okay. Anybody else? Anything else? Any other
No,
answer?
it will be B or A. Little
Okay, so Supriya feels
confused.
it should start with sedimentation. Fine.
Yes.
ML?
Option B would be the correct one, I guess.
Okay. Okay, ML doesn't have any idea. Fine. Cool. So let's see what is there. So it's basically groundwater, and plus it has got excessive iron, carbon dioxide, and odor. So these are the three things which is mainly there. So let's see. The answer, Rahul, is right. The process, so this is directly from our lecture, which is there, groundwater with excessive iron with dissolved carbon dioxide and odor. We have discussed that we need aeration, rapid mixing, flocculations with sedimentation, rapid gravity, pressure filter, and disinfectant. So this is what was there in the lecture which was there. So let's try to reason out why this is required. So Supriya, starting with why sedimentation is not required for this. So this does not, it cannot start with sedimentation. Sedimentation is required, but since we are mainly talking about iron content, carbon dioxide and odor means some amount of organic impurities are also there. So before that, we first need to do flocculation, and only after that we can do sedimentation. That is, we need to increase the size of these particles so that they settle down. Directly settle down, to settle down, you don't have much suspended impurities which are there in this particular one. So sedimentation would come at a later stage. So before that, there are other methods which we need to do. Right. So we are starting with aeration because we have already learned that to remove odor, aeration is a method that we use to keep the freshness of water. We add this impure, we add oxygen, or we add this so that bacteria and all can be removed from this. So aeration provides oxygen to bacteria for treating and stabilizing wastewater. So oxygen is needed by bacteria to allow biodegeneration to occur. The supplied oxygen is used by bacteria in the wastewater to break down the organic to form carbon dioxide. So this is the process of aeration, which is explained over here in this slide. So we have also learned in our slides in the lecture that aeration is the main process which we used in order to remove odor and taste. We add dissolved oxygen and we keep the freshness of water. So that is mainly what is over here, to maintain the freshness of water. Now, followed by this, we do a rapid mixing for this, and then we do flocculation. And why do we do flocculation? Is so we use a chemical coagulant, and so that we create larger aggregates which are easy to separate. So for this particular one, we need to increase the size of the particles which are there. So we do flocculation, and after flocculation, we do sedimentation so that these settle down. And after we do sedimentation, we do rapid gravity or pressure filtration. So this we have discussed. So in rapid gravity filtration, so this can either be a slow or rapid process, but it's called a rapid gravity filtration. So it can either use gravity, so then from top we pour it and it gets filtered and comes, or we can use pressure filtration where we increase the pressure difference, and by forcing out water to go through a particular filter, we remove that also. So yeah, so these two methods can be used. And finally, we go with the disinfection. So for this particular question, the the answer is aeration followed by rapid mixing, flocculation, and then sedimentation, rapid sand filtration, and chlorination. Fine? Is that clear? Okay, I'm proceeding further. So this is something which we have learned for our water treatment unit in the lecture. So let's try to see what these are. A, B, and C, D, E, F, we need to find what these are. So any guesses for this one? Rahul says it is D. Okay. Anybody else? ML also says it's D. Okay, right. Fine. So looks like D is the right answer. So let's just see how. So this is what we learned. So basically, first we have the plain sedimentation tank. So water goes here. So this is the plain sedimentation tank, and then it goes to a flash mixer where the rapid mixing happens, which we discussed like before. And then you have the flocculation basin where where flocculation happens, and then you have a settling basin. And over here you have the scrub where all the heavy particles settle down, and you can so you have a scrub to catch that, and then you have a rapid gravity filter which is happening there, and finally chlorination is happening over here, and you have a wash water tank which is used for backwashing of this water, backwashing of these filters to remove the impurities which are settled over them. So yes, so D is the right answer. So you have a sedimentation tank, and then you have a flash mixer for flocculation basin, and then you have a settling basin, and then you have a rapid gravity filter, and then you have a chlorinator over there. So yes, D is the right answer. Let's proceed further. Which factors influence sedimentation of particles during the treatment of water? So this is again, yeah, multiple answer question. So does temperature of water influence the sedimentation process?
Yes.
Yes. Why? Because why does it influence? Okay, so as temperature of water changes, water expands a bit also, right?
Flow,
So,
flow
sorry.
of the particles, speed and all, it depends on the
Exactly,
temperature.
exactly. It increases the motion. So there is some motion which is happening when the temperature increases. So when we are doing sedimentation, if the temperature of water is increased, then it influences. Is viscosity influenced by it?
Yes.
Yes, viscosity is also influenced because again, the same thing. It influences the the whole motion also. And pH of water, does that influence sedimentation?
Yes.
pH of
No.
water influence. Okay.
No. No.
Okay. So pH is an indicator of whether what the it there are presence of acids or there are presence of bases. So that may not influence sedimentation because it's just a property of water. It's a property of water, and the impurities uh, it is not influencing. And density of water, does it influence?
Yes.
Yes, density, because based on relative density only, the overall sedimentation process can be done. So based on this, our answer would be it's A, B, and D, right? So option A, B, and D. So this is again from the lecture what we have learned. So here we have discussed about factors influencing sedimentation. So we have discussed about viscosity, density, and temperature of water influencing, but pH does not influence, right? So A, B, and D is the answer for that. Fine. So now let's go to the next question. A typical length to width ratio for rectangular sedimentation tank is?
A 3 is to 1, 5 is to 1.
Yeah, so this is a very simple question. This is directly from our lecture. We have already learned that, so it doesn't need much explanation. So we have learned that for a normal rectangular pumps, a typical pump, the ratio is always 3 is to 1 is to 5 is to 1. We also learned about how these, sorry, yeah, how these tanks are made, how different uh, supports are given so that water can be channelized easily. We also learned about the capacity of water also, which is required. So in the interest of time, I'm proceeding further to the next question. Which statement is incorrect regarding sand filters? The depth of the sand bed should be between 60 to 90 meters. Is that right? We have learned about sand filters. So should the depth of the bed be between 60 to 90 meters?
Yes, it is right.
It is right. Fine. Sand media should be supported with a gravel bed.
Yes, correct.
That also we have learned. Yes, it should be supported. Now, the effective size of sand particles in the sand bed in a slow sand filter is less than that of rapid gravity filter. This is,
Yes, size is less in this slow filter.
are you sure?
1 second.
You're right. So the size in a slow sand filter is about zero point 0.3 to 0.35, whereas in a rapid gravity filter, it starts from 0.35 to zero point 0.5. Like that is the size limit. We've learned that. And why? Because if this is it, why? Can you reason out why this is happening?
Yes, because in slow sand filter, if the particles are small, then filtration will happen in a better way. And in the rapid gravity filter, it depends on the gravity. So larger particle size can also help in filtration.
Okay, yes, it can help. Now, why mainly it's happening is because this is in a rapid gravity filter, it happens at a very high velocity. Or
Yes, yes,
yeah,
that is
so when
also
you
there.
have a higher velocity, like you're pushing on something, so you need more filtration.
Voids,
Yeah,
bigger
exactly.
voids is required.
Yes, yes, exactly. Now, the last one, rapid gravity filters do not require backwashing. Is that right?
Mm, I think it's required. I think in both the filters, the backwashing is required for slow and
Wrong. Yeah, so that is right. So Rahul says that, yeah, so all the filters you backwashing is a must. So this is wrong. Like, do not require is it is required. So now just to explain this further, we have already discussed this. So this is what we were saying. This should be between 60 to 90 centimeters. So that we have discussed that it should be between 60 to 90 centimeter. And after that, there is a gravel bed which is supported. So how does it help? Because it helps the movement of unfiltered water to the under drain. So there are these under drains. So this gravel bed is used so that it can move these to the under drains, and from the under drains it is taken off. So this, and yeah, so the size of the particles also we just discussed now, from zero point 0.3 to 0.35 and 0.35 to zero point 0.5. Fine. So yes, so the last option D is the incorrect statement. Now question 14. In rural areas, disinfection of water in wells and ponds is performed by adding which of the following? Iodine.
potassium.
Okay, potassium permanganate is what Supriya says. Okay, Rahul also says. Now, why not iodine? Why not iodine? We have learned that iodine can also be used, and iodine and bromine are found in the pill format and it's easily available. So, why is it not used in rural areas? Okay, why not iodine? We'll come back to that. Why not lime? And why not
Because it
chlorine?
makes lime makes it more acidic, and chlorine is to keep only if the water is so much infected with bacteria, we use chlorine. Lime will make it acidic.
Very good, very good. That reasoning is absolutely right. So lime has this problem. So lime, uh, we can use it in order to remove hardness of water. This we have already learned. And excess lime, if we are adding, then we can remove bacteria also. But this will increase the pH of the water. So that ends, it is not preferred in anywhere. Like nowhere, it is actually preferred as a disinfectant for a large consumer portable water supply. It is not used. And chlorine, yes, it mainly removes the bacteria. And for iodine also, similar to chlorine, it kills the bacteria. Like the whole idea is that it kills bacteria. But we've already learned in our lectures, we discussed that in rural areas the problem is that the water which we have, because of lack of proper sanitation and pumping of water and all that, because of certain unhygienic conditions, the water need not be that good. Whatever we are getting it from the wells or ponds itself will be contaminated with organic waste also. So in that case, our this one iodine will not be sufficient for that, whereas potassium permanganate will be more sufficient in that aspect, and it's easily available also. So due to this, so this is commonly used in rural areas, right? So
Can you
now,
please tell me again why potassium is used, potassium permanganate is used
no,
in
because
villages?
potassium, yeah, so that's what. So we are ruling out the other things in, so over here, potassium permanganate has the ability to oxidize organic matter also. Like, so this oxidizes organic matter, and we just need to add about, like we learned this, like about 1 to 2 milligram per liter and that is adequate enough in order to even oxidize organic matter and kill bacteria. So in rural areas, the problem is there is more organic waste or like there are we in if you remember in our initial lectures itself, we had discussed about water quality, and there we were talking about how we reduce the water quality standards in rural areas because because in rural areas we cannot expect the water quality to be of the actual standards which we give in city because of the conditions over there. uh, so as discussed, like there has not been much standards which can be used over there, because the overall water quality in general is a bit less, and the facilities are also a bit poor over there, so there's mostly this mixing of organic material into water that is also there. So this water is highly rich in organic matter also, so we need to remove that also. Whereas iodine mainly focuses on removing bacteria, that is, it kills the bacteria only, but other organic components which can be present in it also needs to be removed, which potassium permanganate can do. So hence it is commonly used in rural areas. Is that clear?
Yes, thank you.
Fine. So let's go to the last one. That is, match the following and mark the option for the correct match. So we have spray aerators, waterfall aerators, and cascade areas. So which of these, which is which? So water falls from the edges of trays to a collection tray. Is that spray or waterfall or cascade aerator? Okay. Trays to Rahul says R3. R is 3. Water. Yeah, R is 3, right? R is 3. And the other two, waterfall aerators and spray aerators. P is 2, trays to collect artificially created water droplets, yes, and mist, yes, correct, absolutely correct. And the other one, waterfall aerators, water falls from edges into the collection tray. So that comes up to our option C, right? Yeah, option option C, correct. Okay, so I think we have our time has ended right now. I think I had one more question, which, but yeah, so that it's directly from the lecture only, so I'm not going into that. We've already exceeded the time. So that's all for today's discussion. It was nice interacting with you. If you have any doubts, you can ask now for this lecture or the previous lecture, or anything you can ask now. Any doubts? No. So, Supriya, I see in the discussion forum you had asked about question number 7, is it? Question number 7 of the previous assignment. Is that
Yes.
cleared?
No, it was assignment 5, I guess.
Yeah, assignment 5. Okay, I'll just share my screen. That submission is over, right? But the results are not out, is it?
I think results are out.
Results are out, but solution is not out. Okay.
Yes, solution is not out.
Okay, okay. I'll just share that screen with you. Yeah, so this is the question that you asked, right? This one.
Yes, yes, yes.
Okay. So what was your doubt? So basically, so we have P, Q, and R. So let's try solving this. So what is P?
P will be tree.
Okay, P is 3.
Uh,
Okay, then
Actually, see, Q is radial, it's correct.
okay.
But actually, I forgot what was the issue with this question.
Okay, R is interlaced. So rectilinear, interlaced, iron grid, all this is the same only,
Yes,
known by
yes.
different names. So we have discussed that before. So yeah, so this is pretty straightforward. So P will be 3, Q will be 1, and R will be 2,
Yes,
right?
it is clear, but I forgot is I if I have written this right query or it was some other.
Where you okay, so you look into that, and if there's something
Yeah.
put, we can discuss it in this class, or we can or we'll answer it in the discussion forums also. Some one person might answer.
Yeah, no issue. Actually, I have one thing to tell. Actually, two your solving session goes on. One is yesterday, Monday, and then today is yours.
Hmm.
So many questions are repeated.
Yeah.
So I guess if it doesn't happen, then it would help
Oh,
us.
okay. Yeah, no, the idea is that actually, yeah, I understand your concern. The thing is, there's only one problem session which is actually scheduled for one course. But for this session, considering the high number of participants which were there, two sessions we are keeping. So the idea is it will be repetitive. It is we are discussing the same questions only. Basically, we are discussing the previous assignment questions, which was there in
All
the
right.
last run. So that
Okay.
is there's that limited set of questions which are there. So that's what, and most of the questions, like especially like what happened today, most of the questions we are able to discuss in one session itself. So in case some of the questions are left, then we can carry it forward and we can take the next questions. But since we're doing most of the questions, it is repetitive. So it's advisable that you can join any one of the session. That would be adequate. It's not necessary that you should join for both of the session. And when it
Okay.
comes to some problems, extra problems, if you remember, like sometimes I make a point of that we do a different, more questions on problem solving and all also, so that if most of the problems are covered, then rather than repeating, we try to do different set of problems also. So that attempt also we are making. But as per NPTEL requirement, it's ideal that you need to attend only one session. You need not attend both the sessions.
Okay. All right.
Right. Okay. So if that's it, we can wind up for today. No more doubts. Fine. Thank you for being very energetic and good participants here now. So we'll see you all next week then. Yeah. Bye bye.
Thank you.
Take care.
Bye.